In this video, we're going to talk about the product and chain rules for taking derivatives with parameterized vector-valued functions. So just to go over the rules really quick, our product rules should look fairly familiar to you. So if we're taking the derivative ddt of the dot product, for example, of two vectors, then this is the same as taking the derivative of the first, dotting it with just the second, and then adding to it the first left alone, dotted with the derivative of the second. Okay, so that's for that dot product. We can also consider the case where maybe we have some scalar function, we'll call it alpha of t, so this is just your regular old function, and we want to multiply that by our vector valued function u of t. So same idea as the one with the dot product. We take the derivative of alpha of t times u of t has been left alone, and then add to it alpha of t times the derivative of u of t. Okay, so again, which is the same pattern of derivative, left alone, derivative. And then the other type of product we can consider is a cross product u of t cross v of t. And you may already be able to see where this is going. We have u prime cross v plus u cross v prime. Okay, and I do want to point out that since we're working with the cross product, which does not commute, that the order of u and v is really important. So make sure that you keep track of that as you go through those types of problems. The other thing I just want to highlight is, like I've said, notice that these are all kind of the same idea following what we know to be the product rule that we may have learned in Calc 1. Which was that if you have f times g and we want to take the derivative of that, we take the derivative of f, multiply it by g, and add to it f times the derivative of g, okay? We also have a chain rule for these types of functions, and it is very similar to the chain rule that we learned for working with scalar functions. So our chain rule looks something like this. So we're taking the derivative of a vector valued function that maybe in each component we went ahead and plugged in an extra scalar valued function. Then one option to be able to evaluate this is to take the derivative of that scalar valued function and then multiply it by the derivative of the vector valued function with that inside function still plugged in and completely left alone. So I'm going to go through and work an example for each of these. So for our first example, I'm going to let r1 of t be equal to t cubed cosine 3t, and then sine of t, and then my second one is going to be, let's say e to the t, e to the 2t, and then e to the 3t. And for this first example, we're just going to look at using the dot product rule. So we're going to find d dt r1 of t dotted with r2 of t. And I'm going to find this two ways. The first way is going to be to actually use the product rule. And then the second way is going to be to take product first. And then I'll take the derivative the way we normally would. Okay, so let's do this the first way. So method one. In this case, this expands out to d dt of applied to r1 of t, and then r2 of t, and then plus r1 of t left alone times d dt of r2 of t. Just like so. So if we wanted to look at this guy up here, we would take the derivative of r1 of t, which is 3t squared, and then negative 3 sine of 3t, and then, oops, these should be dot products here, and then cosine of t, like so. It looks like I'm going to run out of space on my page there. This guy is dotted with r2 of t left alone, so e of t, or e to the t, e to the 2t, e to the 3t. And then we want to add to that r1 of t left alone, so that's just going to be t cubed cosine of 3t sine of t, and then dot that with the derivative of r2 of t. So that's going to be e to the t, because e to the t, take the derivative, you just get e to the t back. Apply the chain rule to just this piece right here, and you're going to get 2 e to the 2t. And then same idea here, we get 3 e to the 3t. If you go through and take all of these dot products here, what you're going to wind up with is your final result then is going to be dot product of these two guys right here. You're going to get 3t squared e to the t plus, and I guess that actually winds up being minus, because you're going to have minus 3 sine of 3t e to the 2t, and then plus cosine of t times e to the 3t. And then for our second dot product, we are now going to add to this t cubed times e to the t, and then plus, I'm going to get 2e to the 2t cosine of 3t, and then finally, those two components match up, we get 3e to the 3t sine of t. So that's these two guys added together. And so that's this first way of doing the derivative of a dot product, where we use that product rule like so. So to do it the other way, we can apply that product first. So and rewrite this as d dt t cubed cosine 3t sine of t dotted with e to the t, e to the 2t, e to the 3t, like so. Taking this dot product, we're going to get d dt of t cubed e to the t plus e to the 2t cosine of 3t plus e to the 3t sine of t. And then now we just have to take the derivative of this the way that we normally would. So again, reaching back to the rules that we learned in Calc 1, we're going to apply the product rule to each of these terms, and you get 3t squared e to the t plus t cubed e to the t. So that takes care of this first one here. Our second one is going to be 2 e to the 2t times cosine of 3t, and then plus, now we have to take the derivative of that cosine first, which is actually going to give us a minus 3 e to the 2t sine of 3t. So this 3 came from the inside here, doing the chain rule with that. And then we have to take care of this last term here, and you get 3 e to the 3t sine of t plus, oops, no 3, e to the 3 of t, 3t, and then that sine of t, when we take its derivative, we're going to get cosine of t. And so then that pretty much winds up being it. If you want, you can take the time to go through and rearrange all the different pieces in this versus the other answer we got, and you should get the same thing using both routes. So you can do it either way, and you'll get the same answer. So for our next example, we are going to look at letting r of t be equal to that e to the t, e to the 2t, e to the 3t. And what we're going to do now is apply the, not the chain rule, the product rule when we have a function times this vector right here. So we'll take d dt of, let's say, natural log 2 plus t cubed times r of t. And we are going to find this using both methods. So for method 1, what we can do is take this and multiply it through each one of these things here. Or rather, actually, method 1 is using the product rule. I got them backwards. So to be able to do that, we're going to say that d dt of the natural log 2 plus t cubed times r of t is equal to d dt of the natural log of 2 plus t cubed times r of t plus natural log of 2 plus t cubed d dt r of t. So taking the derivative of this piece right here, natural log means that whatever's inside goes on the bottom. But then chain rule says that we have to put the derivative of this on top. So we get 3t squared, like so. And then this gets multiplied by r of t, which is e to the t, e to the 2t, and then e to the 3t. And then we add to it the natural log of 2 plus t cubed times the derivative of r of t, which is just going to be e to the t, 2e to the 2t, and then 3e to the 3t. So that's our first option for being able to do this. The other method that we can take would be to compute the product first. So we'll have d dt of, you wind up with the natural log of 2 plus t cubed times e to the t, and then natural log of 2 plus t cubed times e to the 2t, and then natural log of 2 plus t cubed times e to the 3t. So we'll just take the derivative of each of these pieces individually. And what we're going to wind up with in this case is we're going to have to use the product rule on each one of these guys right here. So we take the derivative of this first and then multiply it by that. So the derivative of natural log of 2 plus t cubed, we just computed it right here. That's that 3t squared, 2 plus t cubed. And then we still have to multiply by e to the t. And then we add to it natural log 2 plus t cubed times e raised to the t, because that's the derivative of the second piece. And then I guess I'll put each of these components on a different line here because we're going to run out of space. Same idea for the second component here. Take the derivative of the natural log 2 plus t cubed. You get that 3t squared over 2 plus t cubed, but then we still have to multiply by e to the 2t, and then add to it the derivative of this piece times this piece left alone, e to the 2t, and then that takes care of the derivative of the second component here. And then finally for our third component, which is going to go on yet another line, we apply the same idea, derivative of this piece times that piece, plus derivative of the e to the 3t times that. So you get 3t squared 2 plus t cubed. So that's our derivative of the first half. Multiply in e to the 3t. And then we have to add to it natural log of 2 plus t cubed left alone times, when we took the derivative here, we want 3e to the 3t, like so, which means that we also need to add in a 2 right there, because chain rule. So that's how you work with these scalar valued functions multiplied by the vector valued function. Our next example is a little bit more involved. We're going to work with the cross product. So again, we're going to do R1 of t equal to that t cubed cosine of 3t sine of t, and then R2 of t equal to e to the t, e to the 2t, e to the 3t. And for this one, we are going to compute d dt of R1 t cross R2 of t. We're going to do this both ways. So method 1. We are going to take dt of R1 t cross R2 of t and say that that is equal to d dt R1 of t cross R2 of t left alone, and then plus R1 of t cross d dt of R2 of t, like so. To be able to do this, we just take the derivative of that R1 of t, which is, oh man, that should be a t cubed up there. Okay, so 3t squared, and then we get minus 3 sine of 3t, just like we did before, and cosine of t. And then this is crossed with R2 of t, which is e to the t, e to the 2t, e to the 3t, like so. And then we add to it R1 of t, t cubed cosine of 3t, sine of t, crossed. Sorry, I've got to do that on 2 lines there. Derivative of that next one there, so e to the t, 2e to the 2t, and then 3e to the 3t. So for this one, I'm actually probably just going to leave it to you to be able to take the cross product of each of these pieces. Although in my next piece here, I'll show you kind of how that works, taking the cross product of the 2 functions. So call this a fun exercise. Yay. Okay. So for our second method then, we take the cross product first. So what does that look like exactly? So again, just to remind yourselves, d dt of R1 of t cross R2 of t. So R1 of t cross R2 of t. So we apply the exact same idea as we have with cross products in the past, and we look at the determinant of I hat, j hat, k hat, and then the vectors go in the rows. So you get t cubed cosine of 3t and then sine of t, and then e to the t, e to the 2t, and then e to the 3t as that last row there. If you take this determinant, what you are going to get is I hat times cosine of 3t times e to the 3t minus sine of t times e to the 2t minus j hat times t cubed e to the 3t minus e to the t sine of t, and then plus k hat times t cubed e to the 2t minus e to the t cosine of 3t. So just kind of cleaning this up a little bit, what you're going to get out of it is going to be e to the 3t cosine 3t minus e to the 2t sine of t I hat minus t cubed e to the 3t minus e to the t sine of t j hat, and then plus t cubed e to the 2t minus e to the t cosine of 3t k hat. And so now all we got to do is actually just go through and take the derivative of each one of these pieces here. I'm going to go ahead and keep the I hat, j hat, and k hat notation just to kind of, I don't know, keep things a little bit cleaner, I guess. So if we want to take the derivative of R1 cross R2, we are going to get, all right, here we go. 3e to the 3t cosine of 3t. And then this guy requires the product rule, so we're going to have minus 3e to the 3t sine of 3t. And then product rule here too. So minus 2e to the 2t sine of t plus e to the 2t cosine of t. Okay, now that finishes everything in the I hat part. So I'm actually going to use some square braces here just to kind of help keep that a little bit cleaner. Now we have the j hat part. So we have that minus still. I'm going to open some square brackets here. We're going to get 3t squared e to the 3t plus 3t cubed e to the 3t. So that's that first term. Minus, open some parentheses, e to the t sine of t plus e to the t cosine of t. All right, that's all of j hat. And then finally, plus square brackets, we have 3t squared e to the 2t plus 2t cubed e to the 2t. So that's this piece here. And then minus, open some parentheses, e to the t cosine of 3t plus, actually that winds up being minus 3 e to the t sine of 3t. And then that's everything for k hat. So this all right here is the derivative of R1t cross R2t. And if we want, you can kind of go back to what we did earlier with this version right here. Take all of these cross products and double check to make sure that it matches what you get over here. But I will leave that part to you. So. Now, for our final example, we are going to look at a chain rule. So let's say that we have f of t equal to e to the 2t, and we are going to work with r of t equal to t cubed cosine of 3t, and then sine of t. And we are going to find d dt of r with f of t plugged in, like so. So once again, we can use our two methods, the first of which being to use the chain rule. And in this case, d dt of r of f of t, 2, 3, is equal to f prime of t times r prime of f of t. Okay. So maybe in this case, it's easiest to just kind of split this up into two pieces here. We're going to take this derivative first, followed by this derivative, and then I'll plug this back in. So f prime of t is straightforward enough. It's just 2 times e raised to the 2t. And then r prime of t is equal to, as we've said before, 3t squared, negative 3 sine of 3t, and then cosine of t, like so. So all we got to do is fill in the pieces for this formula right here. So d dt of r of f of t is equal to 2e to the 2t multiplied on the outside by 3, and then this f of t here is going to go in for t. So we're going to get e to the 2t squared, and then minus 3 sine of 3 times e to the 2t, and then cosine of 3e to the 2t. This is e to the 2t. So that's pretty much all there is to do with that one right there. If we wanted to look at our second method, so take the composition first is what that would look like. So then d dt of r of f of t becomes d dt of e to the 2t cubed cosine of 3e to the 2t, and then sine e to the 2t. So to be able to do this one right here, what we're going to wind up with then is you're taking the derivative, just to simplify this a little bit, e to the 6t cosine 3e to the 2t sine e to the 2t. So we take the derivative of each one of these pieces, we get 6e to the 6t. This guy right here requires a chain rule applied just the way that we normally would, and you get 6e to the 2t, and it's actually going to be negative 6 because that 3 comes to the outside, and then the negative comes from taking the derivative of the cosine there. So negative 6e to the 2t sine of, and then the inside stays untouched. And then we apply the same idea here with the chain rule. You get derivative of the inside times the derivative of the outside with the derivative still plugged, or with the inside still plugged in, just like so. And just like you could in the previous ones, you can double check to make sure that this is equal to the result that we get in using the actual chain rule. So that's pretty much it to being able to use the product rule and the chain rule for derivatives of these parameterized vector valued functions. It's, like I said, it's pretty straightforward. A lot of the rules are quite similar to things that you are probably already pretty comfortable with. So that's pretty much it for this video. I will see you next time.